The Compton Spectrometer and Imager, or COSI, is a wide-field telescope. It's designed to study the sky at gamma-ray energies.
As Dr. Steve Boggs explains, the person in the interview and one of the authors of the 2016 super pressure balloon flight of the Compton Spectrometer and Imager, COSI, is a device used to observe gamma rays generated by astrophysical sources such as stars in the deep universe. The gamma ray image and spectrum can be used to study the emission of stellar nuclear lines. From that, scientists can determine the location of the gamma source, the stage of life of a star, its composition and temperature, and more. Such data are critical to understand the universe and its history of evolution. To understand Compton scattering and how COSI works, the principle of a working camera is a good example to start with. Inside a camera, multiple layers of lenses are assembled to capture light and focus images. As an incident photon enters the camera lens at a specific angle, it refracts at some specific angles and lands on a specific pixel on the image sensor. The camera can then map each pixel's data and generate an entire picture. Cameras use photoelectric effect image sensors to detect light rays. COSI uses Compton scattering effect pure crystal detectors to detect gamma rays. Similar to camera lenses, COSI is composed of multiple layers of pure germanium crystal. As the gamma ray enters and interacts with the pure germanium crystal detector, Compton scattering occurs. An event like this is recorded with all of its information regarding scatter angles, energies, and absorption probabilities. According to Kieran's and Boggs' paper, 888 detector strips are read out individually through a low-noise, low-power analog signal processing chain. It's then split into two pulse-shaped amplifier channels, a fast channel to record timing, and a slow channel to record energy. Compton scattering ends up in a specific scattered angle. However, its orientation is arbitrary, resulting in a cone of possible incoming photon tracks. The origin of a gamma ray can be restricted to an event circle. According to a 2006 paper, the Compton Impaired Creation Telescope MEGA, once the interaction points are known by their physical properties, the interaction itself can be reconstructed. There will be a complex algorithm which is used to filter the Compton and pair events, sequence the interaction points, and finally reconstruct the original photon. By taking multiple measurements of different photons, the event circles will eventually overlap at one point, the point of the original gamma source.
By studying their gamma ray emissions, we can study where in our galaxy today new elements are being created. And we're the first instrument that's designed to be able to directly image the annihilation of positrons in our galaxies.
May 17th, 2016, New Zealand, Wanaka. Dr. Boggs and his team set out for a high-altitude balloon COSI mission. Gamma rays are extremely important in revealing the cosmic emission event. Yet, it was the least explored spectrum range in the field of astronomy. The balloon flight would validate COSI's capabilities and offer groundbreaking observational work. During the mission, COSI was installed, and the balloon was released to high altitude and circulated around the Antarctic for minimal atmospheric interference. After 14 days of in-flight surveying, the mission was concluded more than a month later, and the team was able to retrieve the instruments and, of course, the data for analysis. According to NASA mission website, COSY is a NASA-funded mission designed to probe the mysterious origins of galactic positrons, study the creation of new elements in the galaxy, and perform pioneering studies of gamma-ray bursts and black holes. The 2016 balloon flight gathers some valuable data. In particular, regarding galactic positrons, the 511 kiloelectron-volt emission is the strongest persistent galactic gamma-ray line signal. The team was able to isolate the emission from instrumental background and states that this is the first detection of the positron annihilation signal from the galaxy. Regarding the creation of elements, most aluminum-26 originates in massive stars and core collapse supernova nucleosynthesis. The team concludes the framework behaves as expected and returns a 3.7 sigma measurement above background. And the result is key proof of concept for future studies. Furthermore, regarding gamma-ray burst, COSY enables the study of the polarization of gamma-ray bursts in bright gamma-ray compact objects such as the Crab, Cygnus X1, and Centaurus Alpha, leading to further understanding about the emission mechanisms and magnetic field ordering in these systems. However, the results from the 2016 balloon flight were preliminary work that requires further study. The image and spectrum need to be analyzed to determine the source of the gamma ray, as the preliminary data has yet to confirm or imply inconsistency, should there be any, with the theory that we already have.